hope you feel that last month's refresher course in the fundamentals of electricity and magnetism was useful.
Yeah, I certainly do, Professor. I'm sure the review of that information will help all technicians to understand automotive electrical systems better. And speaking of technicians, you'd be surprised how they keep me on my toes, answering some of their questions. In an electrical session the other day, for example, one of them asked me just how the thermal electric gauges in the instrument panel worked and how to troubleshoot them. How would you handle that one?
That's a good question, Tech. To understand the thermal electric gauge system, you've got to consider not only the gauge itself, but the entire gauge circuit, the voltage limiter, the gauge, the sending unit, and the connecting wires.
Right. And judging from some comments I've heard, a few of our men aren't quite clear on just why we have the voltage limiter in the circuit, or how it does its job.
That's an important point, Tech. This is the way I'd explain it. During normal operation, the voltage available from the car's electrical system varies considerably depending upon alternator output, battery condition, and the electrical load. But the thermal-electric gauge system requires an average voltage that doesn't vary if gauge indications are to be accurate. So, in effect, the voltage limiter takes whatever voltage is available from the battery or alternator and reduces it to 5 volts for use in the gauge circuits. If you could see through the cover of a typical voltage limiter, you'd find an electric heating coil wrapped around a bimetallic arm that opens and closes a set of contact points. These are the working parts. Here's how the voltage limiter operates. When the ignition switch is on, current from the car's electrical system flows through the contact points and the bimetallic arm to the rest of the gauge circuit. At the same time, some current also flows through the heating coil to the ground. The current flowing through the heating coil heats the bimetallic arm so that the arm bends. This opens the contact points and breaks the circuit through both the heating coil and the arm. When the heating coil cools, the arm straightens out, closing the points and starting the cycle once again. The rapid opening and closing of the points provides a pulsating current at a controlled reduced voltage for the gauge circuit.
Okay, you've described how the gauge system is supplied with an average current at a controlled voltage, despite variations in the car's electrical system. But what happens next? How is this current put to use?
Inside the gauge, there's another heating coil wrapped around a bimetallic arm. This arm is linked to the gauge pointer so that the pointer's position is determined by the temperature of the arm. When there's only a slight current flowing through the gauge heating coil, the arm doesn't bend very much. Consequently, the gauge pointer moves only a little bit. But with increased current, the heating coil gets warmer and the arm bends more, moving the pointer to the other side of the gauge dial. And that's how the thermal-electric gauges operate.
You're doing a fine job of explaining the gauge system so far. The next question that usually comes up is, how is the current flow through the gauge regulated so that the gauge will show the proper reading?
As you know, that's done by a variable resistance in the sending unit, Tech. Inside the fuel level sending unit, for example, is a grounded contact arm that moves along a coil of resistance wire. This resistance unit and the contact arm are in series with the gauge. The position of the movable contact arm is controlled by the fuel tank float. As the tank empties, the float moves the contact arm so that the current passes through nearly all of the resistance wire before it goes to ground. This high resistance results in only a slight current flow through the circuit, so the gauge heating coil stays cool and the gauge indicates a low fuel level. On the other hand, when the tank is full, the float rises, moving the contact arm so that the current passes through only a few turns of resistance wire before being grounded. Since this reduces the resistance in the circuit, there's increased current flow which raises the temperature of the gauge heating coil, and as a result, the gauge reads full.
Well, that covers the fuel level sending unit all right. But what about the one for engine temperature?
The engine temperature sending unit does the same job of varying the resistance to current flow in the circuit. but it does the job in a different manner. A resistor in the sending unit is made of a special material which has high resistance when it's cold and low resistance when it's hot. The resistor is located where it can sense engine coolant temperature.
There's one more sending unit to consider. The one for the oil pressure gauge in the Imperial and Dodge 880.
That's right. In the Imperial and Dodge 880, the oil pressure sending unit also operates on the principle of varying electrical resistance. This resistance is high when oil pressure is low, but the resistance becomes low when the pressure is high.
All right. You've told the story of how the gauges, sending units, and voltage limiter work. Now, how about covering service tips and testing?
Good idea, Tech. I'd like to start by covering some mighty important service precautions. Only one voltage limiter is used to provide current to all of the gauges, and in some models, the voltage limiter is built right in one of the gauges. You can tell which gauge has the voltage limiter because it's the one with 3 terminals. The terminal marked I is the voltage limiter input terminal. The terminal marked A is the output connection to the other gauges. The terminal marked S is the connection to the gauge sending unit. Proper identification of these terminals is very important, and that's because if you accidentally apply full battery voltage to either the A terminal or the S terminal, you'll burn out the gauge heating coils. So be sure to connect the hot wire from the ignition switch only to the input terminal, marked I. Here's another tip for protection of the gauge heating coils. Never apply full battery voltage to the voltage limiter either in the car or on the bench without first being positive that the instrument cluster is grounded so that the voltage limiter will work, or you'll burn out the gauges. And before you remove the instrument cluster for service, be sure to disconnect the battery ground cable. If you don't, you might accidentally short out a gauge, printed circuit, or some other part and do considerable damage. If none of the thermal electric gauges are working, the trouble is probably in the voltage limiter, in the instrument cluster ground, or in the lead from the ignition switch. If only one gauge is out, check the individual circuit, the gauge, the sending unit, and the connecting wiring. To test the thermal electric gauge circuits, a good voltmeter and the special electronic gauge tester are needed.
Yes, and it's also a good idea to have 2 10-foot lengths of 16-gauge test wire with spring clips on both ends, so you can make the tests while you're sitting in the driver's seat.
The voltmeter can be connected between the temperature sending unit terminal and a ground and used to test the voltage limiter. If the voltage limiter is working correctly, the voltmeter needle will pulsate when the ignition switch is on. When the electronic gauge tester is connected in place of a sending unit, it applies a known resistance to the gauge circuit. Simply disconnect the wire from the sending unit and connect it to one of the tester leads. Connect the other tester lead to a good ground.
Here's something to watch out for. Be careful not to ground the sending unit wire, or you'll cause a high current flow through the gauge heating coil. This is apt to ruin the gauge. Grounding the sending unit terminal will cause the same kind of trouble.
Good tip, Tech. Now, if the gauge reaction is correct when you're using the gauge tester, the trouble's in the sending unit. But if the gauge doesn't read correctly, the trouble is in either the gauge itself or in the wiring.
You'll find all the details for making individual gauge tests for every 1963 car model in the reference book for this session. Now, before we get into some other electrical diagnosis subjects, let's give our instructor a minute to catch his breath while someone turns this record over. Well, that takes care of the thermal electric gauge story. Now, here's a question that's asked quite often. Why is it so important to check battery condition before testing electrical circuits?
It's important for several reasons, Tech. First of all, the battery condition affects the operation of every electrical circuit in the car. In testing electrical circuits, you've got to work with as many known values as possible. Since most electrical tests are based on known battery voltage and condition, the battery must put out the specified voltage. That's the main reason why battery condition is so important to electrical circuit testing.
Yes, and that's also why the battery is the logical starting point for electrical tests on the car. For these electrical tests, an understanding of the circuits involved is important too. Now, last month's session explained current flow through simple series circuits and parallel circuits. But actually, the complete automotive electrical system isn't quite that simple.
That's very true, Dick. The automotive electrical system is a combination of series circuits and parallel circuits. If the technician recognizes these two types of circuits and remembers what he learned about current flow through them, the electrical tests should be easy to understand. Generally, electrical tests involve measuring the voltage and current flow in the circuit, or between 2 points in the circuit, and comparing the readings with test specifications. If voltage and current flow meet specifications, resistance has to be right. Getting back to the battery, if it's not capable of putting out full voltage for the tests, don't just charge the battery or install a new one and let it go at that. Also, make tests to find out why the original battery failed. After all, the battery is only one part of the charging system, so you should also check out circuit resistances and alternator and voltage regulator performance.
I'd like to bring up a big point about these charging system tests right now. Charging system tests have been planned in a logical and extremely efficient sequence. Don't try to shortcut the test sequence by leaving out any of the tests and going directly to the suspected part.
Each test eliminates an unknown or a possible cause of trouble. For example, high field circuit resistance at a bad connection affects the operation of the voltage regulator and prevents it from limiting charging system voltage to the specified value. For this reason, we must know that field circuit resistance is okay before making other tests. Also, this test can be made without disconnecting any wires in the field circuit itself. That way, there's less chance of disturbing any clues if high resistance is caused by a loose or corroded connection.
Speaking of disconnecting wires, how would you explain why it's necessary to disconnect one of the ignition leads from the ballast resistor for this test?
Well, first I'd point out that the test is based on measuring voltage drop in a series circuit. And remember what we said last month about current flow in series circuits and parallel circuits? In a parallel circuit, the total current flow equals the sum of the current flow in each parallel branch. It's easy to see the parallel circuit in this picture, but let's look at the car's electrical circuit. If the ignition lead remained connected to the ballast resistor and the distributor points were closed, the ignition circuit would be completed, and it would be in parallel with the field circuit. The total current flow through the first part of the field circuit would be the sum of the flow in both branches. The added current flow during this test would heat the circuit, increase its resistance, and give a false voltage drop reading. So you can see why it's important to eliminate the parallel circuit by disconnecting the ignition lead from the ballast resistor.
This is one reason why we test circuit resistance first, before the current flow from other tests heats up the circuit beyond the proper test temperature and increases the circuit resistance. That's why the charging circuit resistance test is next.
Right. When you're set up for the charging circuit resistance test, the test ammeter will register current flow in the alternator field windings before the engine is started. This gives you a quick indication of the condition of the brushes, slip rings, and rotor windings. To test charging circuit resistance, we send a known current through the circuit and measure the voltage drop. To produce the known current, use a jumper to remove field regulation and adjust the engine speed to give 10 amperes through the circuit.
Here's what can happen with high resistance in the charging system. The high resistance will cause increased alternator output voltage. But in spite of this, the resistance may prevent full charging voltage from reaching the battery. In addition, it may overwork the voltage regulator.
Good point, Tech. Now let's see what that next test is. After charging circuit resistance is checked out, two more items remain: alternator current output and voltage regulator operation. The alternator current output test is next, simply because voltage regulator tests are based on correct current output.
Can you explain the function of the carbon pile rheostat that's connected into the charging circuit for this test?
I'm sure I can, Tech. With a fully charged battery, the output voltage of the alternator would exceed the specified voltage at the test RPM. So, we connect the carbon pile rheostat in parallel across the battery and adjust it to reduce the alternator voltage to the specified value.
Remember, turn off the rheostat immediately after you read the voltmeter for this test. Otherwise, it would overheat and be damaged. Besides, if it's left on, it will discharge the battery.
Right. And it's important to emphasize that the current output test only checks alternator output against a test standard. It's not a test of maximum output.
Okay, now what's the next test?
The last item in the charging circuit tests is the voltage regulator, but you should never adjust the regulator to compensate for high circuit resistance or poor alternator output. That's a surefire way to bring more serious troubles. When testing the voltage regulator, it pays to be particularly precise. The engine speed and electrical load should be readjusted to the specified settings after the charging system temperature has stabilized, or the test readings won't be a true indication of regulator condition. The first voltage regulator test checks out the operation of the upper set of contacts. This determines how the regulator performs under high electrical loads at low speeds, and it tells if the armature spring tension is adjusted properly. The second test checks out the operation of the lower set of contacts. The voltage increase on this test indicates how well the regulator performs under low electrical loads at high speeds and tells if the air gap is adjusted properly. If there's no voltage increase, the air gap is too small and voltage control will be erratic. If the voltage increase is too great, the air gap is too large and the regulator won't be able to limit alternator output at higher speeds.
Okay, you pointed out how a knowledge of electrical fundamentals can be a big help in diagnosing charging circuit problems on the car. Now what's next?
Let's consider the ignition primary circuit next, Tech. The ignition primary circuit is a simple series circuit. Don't be misled by the ignition start and ignition run portions between the switch and the ballast resistor. They're not actually in parallel since only one portion is in use at one time. The purpose of the ignition start portion of the primary circuit is to bypass the ballast resistor and provide full voltage to the coil for a hot spark during cranking.
Which reminds me, the cranking voltage test is a good starting point for testing the ignition primary circuit.
It sure is. The cranking voltage test not only tells you if voltage to the coil is high enough for good ignition during cranking, it also gives you an idea of the condition of the battery, the starting motor, and the entire starting circuit. However, the cranking voltage test doesn't measure resistance in the ignition run portion of the primary circuit or resistance in the part of the circuit from the coil to the distributor. If necessary, those components should be checked out with voltage drop tests.
And if the cranking voltage test turns up some trouble in the starting circuit, what then?
Deciding where to begin testing the starting circuit depends upon the complaint. Slow cranking, for example, indicates high resistance in the battery cable to the starting motor, or trouble in the starting motor itself. Make voltage drop tests in the circuit first, and if the drop is within specifications, you'll have to bench test the starting motor. On the other hand, no cranking at all usually means the trouble's in the control circuit or in the starting motor. In this case, you'd want to begin by checking out circuit continuity with jumper wires and a voltmeter right at the relay.
When making circuit continuity tests, it's helpful to know the circuit connections and the working details of the relay, so you'll understand just what parts of the circuit you're bypassing with each jumper. Now, that wraps up the highlights of electrical circuit tests. Don't miss the test details in the reference book. You have any final words of advice?
Just one thing, Tech. I feel that the most important single thing for the technician to keep in mind is how voltage, current flow, and resistance are related in every circuit he tests, so that the test results really mean something to him. But say, let me ask you something now, Tech. Do you think I could do a job of teaching your technicians about electrical circuit diagnosis?
Absolutely, Professor. You just have.